Let us finish our discussion of section 1.2, geometric series. A geometric series is a series with a constant ratio between successive terms. A geometric series is this. Now, please do not confuse geometric series and geometric sequence. Here is a geometric sequence. In simple words, a geometric sequence is A, AR, AR square, and so on. A geometric series is an infinite sum of these terms. A plus AR plus AR square plus and so on. Let me give you an example. 6, 12, 24, 48, and so on. It's a geometric sequence. However, 6 plus 12 plus 24 plus 48 plus 96 plus and so on, this is a geometric series. Now, let us consider the following finite sum. K from 1 to n, a times r to the power k minus 1, which is in expanded form is a. Indeed, if k is equal to 1, we raise r to 0 power. So the r component disappears because r to 0 power is 1. So term number 1 is a. If k is equal to 2, we have a r to the power 2 minus 1, means r to first power, plus a r. Term number 3, a r square, and so on. The last term, a r to the power n minus 1. This sum is equal to a times 1 minus r to nth power divided by 1 minus r. Of course, this formula works only if r is not equal to 1, because if r is equal to 1, the denominator is equal to 0. How do we prove this formula? Step 1. Let us denote this sum by Sn. After that, multiply both sides here by r. The left-hand side becomes Rsn. On the right-hand side, a times r is ar. ar times r is ar square. And so on. The last term, ar to n minus 1 times r is ar to nth power. After that, let us subtract this from this. First, let us subtract the left-hand sides. Sn minus Rsn, it's over here, is equal to, and now see what happens when we subtract this from this. Note that many terms will get cancelled. For example, ar minus ar, 0. Ar square minus ar square, 0, and so on. Here is what is left. A is left because there is no a here. So we put here a. Another term which is left is ar to nth power, because there is no ar to nth power here. So on the right hand side, we get a minus ar to nth power. Lastly, Let us factor out here the common term Sn, done. And finally, let us divide both sides by 1 minus r. Here is the formula. Sn, which is this, is equal to a times 1 minus r to nth power divided by 1 minus r. Now examples. Find the sum of these geometric series. In order to solve this problem, we should apply this formula. And to apply this formula, we have to identify A and R. In our case, A is 1, R is 1/2. Why? A is term number 1. Just take a look. This is A. Now, term number 1 means K is equal to 1. If K is equal to 1, the power here is 0. 1/2 to 0 power is 1, so A is equal to 1. It's pretty obvious that R is 1/2. Just look at the formula. Lastly, we apply this formula. A is 1, disappears. 1 minus r to nth power is 1 minus 1/2, n is equal to 5. 1/2 to 5th power divided by 1 minus r. And after all simplifications, the answer is 31/16. Similarly, please take a look at this. Now we have 1/2 to k's power. Looks very similar to this. The difference is here k's power, here k minus 1. What do we do? But again, we apply the following general approach. A is term number 1. Term number 1 means k is equal to 1. If k is equal to 1, this becomes 1/2 to 1st power, so A is 1/2. R is, as before, 1/2. So we apply the formula. Now note that we multiply the whole construction by 1/2, because in this formula we have A. A is equal to 1/2 in this example, so we multiply the whole fraction by 1/2. The answer is 31/32. Guys, any questions here?
If k was anything other than 1, we could still apply the same formula?
Very good point. Probably easiest way to think about it is the following. If k is equal to 2 here, we can do the following. Sum from k is equal to 2 to 5 is equal to sum from k is equal to 1 to 5 minus 1/2. So if instead of 1 we have 2 here, the answer will be 31/32 minus 1/2. Last thing, telescoping sums. This example is actually pretty tricky. First of all, observe that we cannot split each fraction into 2 pieces because this is not equal to this. So then what do we do here? Well, we apply here a so-called conjugate trick. Here's what we mean by that. For convenience, let us switch positions here. Let us rewrite square root of 1 plus square root of 2 as square root of 2 plus square root of 1. Let us rewrite square root of 2 plus square root of 3 as square root of 3 plus square root of 2, and square root of 3 plus square root of 4 as square root of 4 plus square root of 3. Here is what we do next. Multiply top and bottom here by square root of 2 minus square root of 1. Same as here. Multiply top and bottom here by square root of 3 minus square root of 2. Finally, multiply top and bottom here by square root of 4 minus square root of 3. As a result, this expression becomes significantly more complicated. And therefore, question is, why do we do it? Well, you will see in a moment that this trick allows us to simplify this expression dramatically. Please take a look at, for example, this. Think about square root of 2 as about A, square root of 1 as about B. By college algebra, A plus B times A minus B is A square minus B square. Similarly here, A square minus B square. And here, A square minus B square. Obviously, square root of 2 square is 2. Square root of 1 square is 1. Similarly here and here. Of course, 2 minus 1 is equal to 3 minus 2 is equal to 4 minus 3 is equal to 1. 1, 1, 1. These ones disappear. Lastly, observe that square root of 3 and square root of 2 get cancelled. The result is square root of 4 minus square root of 1, which is 1. So this is equal to 1. One can see that we can easily generalize this approach. The sum of these fractions when k is running from 1 to n minus 1 is square root of n minus 1. Here's another example. Find this sum. And by the way, now we have an infinite sum. So what do? Well, we cannot really apply the conjugate trick anymore. There is no plus or minus here or here. So what do? By algebra, 1 over k times k plus 1 is 1 over k minus 1 over k plus 1. If we apply this formula to each term over here, we get the following. 1 divided by 1 times 2 is 1 minus 1/2. 1 divided by 2 times 3 is 1/2 minus 1/3. And so on. The last term is equal to 1 over n minus 1 over n plus 1. Now, let us shift parentheses. Let us put parentheses over here, and so on. Done. Observe that after that, most terms similar to this situation, most terms get cancelled. This is 0, and so on. This is 0. What is left is just very first term, which is 1, and very last term, which is 1 over n plus 1. Finally, as n is a finite sum, by calculus, when n goes to infinity, this term goes to 0. Conclusion, this infinite sum is equal to 1. Let me finish this section with the following exceptionally difficult problem. prove that this sum is lesser than 1 for any integer n greater or equal to 2. Folks, any ideas here?
I would say I would try to, I'm not sure if this is something we're going to discuss later or not, but given my time in a different proof-based class, I would try to solve it using mathematical induction.
Mathematical induction. Unfortunately, mathematical induction cannot be applied immediately here. And the reason is the following. The left-hand side depends on n. The right-hand side does not depend on n. If you try to apply mathematical induction directly, you will get stuck. It is still possible to apply math induction. However, in order to apply math induction, you'll have to adjust the right-hand side first. You'll have to come up with a new inequality, which implies this inequality, and apply math induction to prove this new inequality. Any other ideas?
So something that I would try, knowing that the previous series that we looked at, the 1 over 1 times 2, 1 over, yeah, that one, is equal to 1. We've already solved that.
Okay.
However, something that we can notice is the first term, 1 over 1 times 2, is actually greater than the first term in our sequence, 1 over squared. This process can be applied to every single term. Therefore, this series, the one that we already know is equal to 1, must be greater than the series that we're looking at. Since this series is 1, 1 must be greater than the series that we're now looking at, because this series is greater than the series we're now looking at.
Excellent. It's exactly what we do here. Observe that 2 squared is 2 times 2, obviously. 3 squared is 3 times 3, and so on. N squared is n times n. Note that since 2 is greater than 1, 1 divided by 2 times 2 is lesser than 1 divided by 1 times 2. Since 3 is greater than 2, 1 divided by 3 times 3 is lesser than 1 divided by 2 times 3. And so on. Since n is greater than n minus 1, 1 divided by n times n is lesser than 1 divided by n minus 1 times n. And now let us apply this identity to each term. This is equal to this is equal to this, and so on. This is equal to this. We shift parentheses, done. We cancel out, we get rid of the 0 terms, done. Obviously, what is written here is lesser than 1, and problem is solved. But once again, this problem is exceptionally difficult. If you don't know this idea, it's super hard to prove this inequality. By the way, talking about induction, in order to apply induction, first we have to replace 1 by 1 minus 1 over n, and then apply mathematical induction, which we are about to discuss. Folks, We are done with section 1.2. Think about questions.
Can you scroll down to the answer we got?
Yes, over here.
So as n goes to infinity, wouldn't the right and left side be equal?
Note that here n is not infinity. N is any integer greater or equal to 2. Observe that indeed, if n is any given integer greater or equal to 2, 1 minus 1 over n is strictly lesser than 1. Correct?
Yes.